Okay, so last time we ended with this discussion of this diagram that I've drawn here. So this was something that we did immediately after our description of the invariance of angles in a circle. That being that if you are given 2 points on circle and you choose a point on one of the arcs connecting them, then whatever point you choose, as you slide this point around the circle, actually this angle ACB is the same. Okay, that's what is meant by the word invariance. It means that this angle doesn't vary in measurement. It's actually the same size, regardless of where C is slid along this circle. So that leads to the following picture, where we have a special case. So instead of just picking any 2 points on circle, we select our points in such a way that they are opposite ends of a diameter on circle. So if we do that, then if I select my third point C somewhere on that circle, so one context in which this might come up is say that I draw in some dashed line and I want to construct a right triangle that is that lies, or whose third vertex that is where the right angle is going to be, is going to lie somewhere on that line, then it's going to lie exactly where this thing intersects that circle in question. So from a construction standpoint, how would you construct this circle given a line segment AB? So given a line segment AB, you would construct this circle by bisecting the segment. So you know how to bisect a given line segment. So once you bisect that line segment, that finds the radius of the circle, and that radius allows you to draw the circle itself. So then that allows you to find this point. So then applying that previous theorem on the invariance of angles in a circle, this yields a 90 degree angle, or a right angle, right? So this yields a right angle at C. Okay, and the reason it yields a right angle at C is because whatever these angles that we've split C into have to sum to be those have to sum to be pi over 2. And the reason they have to sum to be pi over 2 is because the alpha and beta in question would have to be the same in that case. Okay. All right. So this is how we get that those actually have to be a right angle, or I should say that those things have to sum to be pi over 2 in the event that we've selected our A and B like this. So this is a right angle at C. So this is a nice way of constructing a right triangle on a given segment that you want to be its hypotenuse, right? So given hypotenuse, given a line segment, this is a nice way of constructing right triangle having that line segment as its hypotenuse. We're going to see that this construction will also allow us to construct square roots. Okay. So this is also going to allow us to construct, using compass and straight edge, the notion of square roots. Okay, so but first, I want to do a second proof of the Pythagorean theorem. Actually, it's a more general fact that leads to the Pythagorean theorem. So Euclid used this situation above to prove the Pythagorean theorem in a different way. Okay, so how did he go about doing this? So suppose that I have a given right triangle in this way. So I've already drawn it in like this, but let's just say I have a right triangle, and this is what it looks like. So I can label these side lengths in the usual way. So angle A, opposite side is little a, opposite side to B is little b, and then this segment opposite the angle at C is little c. Okay. All right. Now, given a right triangle, I could, so I know it looks like I'm doing it backwards because the line is already here, but given a right triangle, I could draw a perpendicular passing through the vertex at C perpendicular to line segment AB. Once I've done that, I'm going to label these angles here. So the angle at A, I'll label alpha. I'll label the angle at B beta. Why is this situation nice? It turns out that these triangles that I'm drawing are going to be similar triangles. So in order to see how these are similar triangles, I've labeled my angles alpha and beta, and I want to investigate what these angles formed at C are. Okay, so if I call this angle, or sorry, this point D, okay, note that by definition, since this dashed line is perpendicular to AB, both of the angles formed at D are right angles, right? And so the question is, what is going on here? Well, I know that in my big triangle, say ABC, I have alpha, beta, and then a right angle. So that right angle is pi over 2. The sum of all three of these angles is pi. And so this means that alpha plus beta must be pi over 2. Right? So alpha plus beta is pi over 2. But then, since this is an angle of pi over 2 size, then what does this angle have to be? Well, it has to be beta, right? Because this forms a triangle ADC that has alpha, a right angle, and so then the only thing here that makes this equal to exactly pi would be if beta is, or sorry, if that angle is beta, so that alpha plus beta would be pi over 2, the remaining thing is pi over 2, and so in total I get pi. Similarly, this is a right angle, so angle BDC is a right angle. And so what needs to happen here is that this angle BCD is alpha. Okay, for the same reason. Okay, because alpha plus beta is pi over 2. All right, thus these are similar triangles. Okay, so thus these triangles are similar. Okay. Now, when I say these triangles, what am I referring to? Well, I'm actually referring to three triangles here, right? I'm referring to my large triangle, ABC. So that's ABC is similar to triangle ADC, and it's also similar to BDC. Okay. Now, I haven't done a good job of showing. Normally, when you want to say two triangles are similar, you want to order the vertices in such a way that it's clear what the corresponding sides are. I don't think I did that. I think I screwed up on the orders here, but that's okay. So I'm not claiming that I did a good job organizing that. But all three of the triangles showing up here are similar because they have corresponding angles that are congruent, right? All the corresponding angles are congruent here. Okay. All right. So, how did Euclid use this to prove the Pythagorean theorem? So now these triangles are similar. Okay. So we'll say that the side opposite alpha in each triangle is short and the side opposite beta in each triangle is long. Okay. Thus, compare triangles ABC and ADC. That is the big triangle and the triangle on the left. Okay, so then what we get is long side divided by hypotenuse. So in the big triangle ABC, long side is B and hypotenuse is C. So that's long side over hypotenuse is B over C. In ADC, that's the triangle on the left, what do I need? Well, I get these two lengths here that I need to give names because I don't have a label for them yet. So we'll call this C sub 1 and we'll call this C sub 2. Okay, oh, there. Okay. All right, and so long side over hypotenuse is B over C, which is, according to this notation now, is C sub 1 is the long side, and the hypotenuse is B. All right. So B over C is C sub 1 over B, which implies that B squared, right, is C times C sub 1. Okay. All right, but similarly, what do I notice? So comparing ABC, the big one, with the right triangle, maybe I'll move on to another sheet so that I have plenty of room here. So comparing ABC with triangle BDC, that's the triangle on the right, I want to consider the short side over the hypotenuse. Okay. So the short side, let's go back and look at our picture here. So the short side in triangle ABC is A, and the hypotenuse is C. In my triangle on the right, the short side is C sub 2, and the hypotenuse is A. And so this implies that A squared is equal to C times C sub 2. Okay. So I have two statements. A squared is C times C sub 2. B squared is C times C sub 1. Thus, A squared plus B squared is C times C sub 2 plus C times C sub 1, since these quantities are equal to A squared and B squared respectively. This is C times, I can go ahead and swap the order, C sub 1 plus C sub 2. But what is that? Going back to our picture. Well, in our picture, the entire length of the bottom is C, which is comprised of C sub 1 and C sub 2. It's actually C sub 1 plus C sub 2 using our notion of adding line segments. So this is actually C times C, right? Or C squared. So I just proved that A squared plus B squared is equal to C squared. So that is another proof of the Pythagorean theorem. Now Euclid actually gives this as a second proof. This is the proof by similar triangles. Apparently, math historians think that actually this was the proof of the Pythagorean theorem that the Pythagoreans used. I believe that is the consensus that this is the proof the Pythagoreans used to prove it. So anyway, does this proof, or is this proof better than Euclid's? Not necessarily. I mean, it's not really any shorter than Euclid's proof. One thing that is nice about this is that it uses similar triangles, and drawing in similar triangles when you can is typically a pretty good approach for various geometry problems. And so, it's nice to see a proof that involves just use of similar triangles, or where similar triangles play an important role. So splitting up triangles like this is a nice tool to have, especially for right triangles. So this is nice for that reason, but it's not necessarily any better than the proof that we did first, which was Euclid's original proof. Now, constructing the square root using compass and straight edge. Now, how to do this? I'm going to revisit this picture. Maybe I should draw another one. So I'm going to cheat and do it backwards. So let's. I'm actually going to fix my radius first, just to make this look nice. Okay, so there's my circle, or part of circle, and here's my diameter of circle. I can okay. So here's A and here's B. Now, this is like I said, I'm cheating here to make the picture look nice. This is not how you would actually go about constructing it. So how you go about constructing it is I just draw in a line segment AB, and then what would I do here? So drawing in line segment AB, if I want to construct the square root of say a line segment L, then what I do is the following. Maybe I shouldn't have even labeled these AB to show you what it is that I'm going to do. So, but I'm going to draw in this picture anyway. So I'm going to say draw in some dashed line here. Okay. All right. What am I doing here? Let's say I want to construct square root of L, where L is the length of some given line segment. Okay. Now, what I think I'm going to do, so that there's no confusion, is instead of labeling these points, I'm not going to label them at all. Okay. And so, how this is done is the following. Let's say that the length in question is this length, L. Okay. What do I do? I take this length L, I take my straight edge, I extend this length L, okay. Now, there's no circle here, right? I'm going to draw that in a second. I extend this length L, and I extend this length L in such a way that this distance is the unit length, 1. Okay, now you see why this is something that you can't be given immediately. You would extend this as need be to unit length here. Okay. Now, once I've extended this part of it, what do? I then bisect the segment I get here to find the radius of this circle, where the other endpoint making up this length L is on one end, and the endpoint I've gotten by extending this line unit length is on the other. This is a diameter. Here's the radius. Again, I would find this radius through bisecting the line segment L plus 1. Okay, so I find this radius here. I draw in that circle. Once I've drawn in that circle, I draw in the dashed line that is perpendicular to my line segment, or my diameter, at this point, right? Constructing perpendicular to a given line segment through a point on the line is something you did in your first homework. So doing that, I draw in this line here, and now I get some point here and some line segment. This is the height of a triangle. If I draw in this triangle here, of course this is a right triangle by that theorem I mentioned at the beginning of class. Okay, and this length is h, and in this construction, this h is the square root of L. Now, a couple of things I want to say here. This is a symbol, right? This is a symbol. What does the statement h is equal to the square root of L mean? What that means is that h squared is equal to L, right? We use this symbol, this radical sign, to say that we're in the situation where h squared is equal to L here, right? It's just notation. Okay, why is this the case? So quickly, because as before, we know that this splits this right triangle into similar triangles. So I can look at long side over hypotenuse. And what do I get? Long side in big triangle over hypotenuse. Long side in the triangle on the left. The triangle on the left, long side over hypotenuse is going to be, not long side over hypotenuse. I don't want the hypotenuse showing up here at all, because all I need is long side and short side. So long side over short side here is L over H. That's in my triangle on the left. Okay, but in the triangle on the right, what is long side over short side? So in the triangle on the right, long side over short side is h over 1. So the two triangles I'm comparing are the one on the left and the one on the right. But L over h is equal to h over 1, which implies, hey, h squared is equal to L. Okay. What does this mean? Well, what this means is the following. So note now we have geometric constructions of plus, minus, multiplication, which I'll write as a times, and division. And taking square roots. Okay? What else can be done? I.e., is there any other operation, we'll say algebraic operation, that can be constructed that is not just a combination of these? So this is a question. But in particular, this underlined bit is important. The answer is no. Nothing else can be done. And so if you know a little bit about irrational numbers, what this is saying is that it turns out that if we define the notion of a constructible number, which we'll do in chapter 3, if we define the notion of a constructible number, the constructible number is one that can be constructed from compass and straight edge using from the unit length from 1 using one of these operations or combinations of these. And if something is not constructed, well then by definition I can't get there from just using these operations. Now, it turns out that, of course, a lot of the irrational numbers that you're familiar with, like square root of 2, square root of 3, square root of 5, those can be constructed. The golden ratio can be constructed. There's a lot of irrational numbers that can be constructed using compass and straight edge, but immediately there's some that can't. All right. So, some of the things that might first pop into your head is like pi, right? Pi, if we define this to be the constructible numbers and we say that the others are not constructible, then pi would be not constructible, for instance. E would be not constructible. Cubed root of 2, would be non-constructible. Okay, so I need to justify our terminology there, and we'll do that later. Because I'm using the word constructible and non-constructible as a shortcut for saying which things could or could not be constructed by compass and straight edge, but that's a little I'm doing some hand waving there, because actually to prove that those words actually mean what I say that they mean or what they mean in English when you say that, I need to do some work there. Okay, but intuitively, this gives, an intuitive answer to the questions of what sorts of things can be constructed, even though I still need to justify what things can be constructed. And unfortunately, a lot of the proofs of that come from algebra that is not super complicated, but it's something that would take quite a bit of going into. And so we're not actually going to go into those proofs of that, but I can show you where those proofs are. But anyway, so that's what I wanted to do for chapter 2. Now there's one thing remaining that we're not going to discuss. We're not going to use this list of axioms I'm about to go over too much here. This is just an idea of what can be done with Euclid's axioms. So as I mentioned, so what I want to talk about now for a second are Hilbert's axioms. So Hilbert's axioms for Euclidean geometry. So mathematicians had noticed that Euclid's development of geometry had some gaps. Okay, so one of the most important things is Euclid correctly identified that the parallel postulate or parallel axiom that's the most important axiom for Euclidean geometry. It is the thing that defines Euclidean geometry. And in fact, as I mentioned before, and we're going to talk about many, many times, there are geometries that exist that more or less satisfy the other important axioms, but they fail the parallel axiom. Okay, and that's what makes them so different in a lot of respects. So the idea is that the parallel axiom is by far the most important bit of Euclidean geometry. Okay, it's the thing that makes it Euclidean geometry. But there are some gaps in Euclid's proof, or I shouldn't say gaps in his proof. There are gaps in his development where the axioms don't. They leave some things up in the air. So, for instance, in the very first construction that we did, and the very first construction that Euclid did, the one of constructing an equilateral triangle. How did you construct an equilateral triangle, right? You had your fixed length, you looked at that fixed length, and you drew two circles, right? So you drew a circle centered at one of the ends of that having that radius, and then another circle at the other end having same radius, and then you use the fact that those two circles intersect. But the thing is that the notion that two circles intersect, in 2 points like that, instead of just 1 point, or instead of not intersecting at all, so that's the 3 possible configurations of circles, right? Unless they completely overlap, in which case they intersect at infinitely many points. Euclid doesn't mention anything about circles intersecting, or the existence of points of intersection of circles. Okay, that's a notion of like incidence. Now, Euclid didn't mention that because he considered it to be completely obvious, but it turns out that if you don't nail down all these incidence relationships between geometric objects, then some crazy stuff can happen. Technically, it's not 100% well defined. So that's just one example. As I mentioned before, Euclid did not define products of line segments as we did. That's actually something that Descartes did later. Products of line segments for Euclid had to do with area. Is another thing. So there's a few things that a few gaps in Euclid's treatment that David Hilbert, around the turn of the century in the early 1900s, maybe like 1890-ish, filled in these gaps by axiomatizing Euclidean geometry in a way that made it 100% identical to the geometry of the plane with coordinates, and that is the real plane, right? Ordered pairs of real numbers. So one bad thing about this is it's long. There's like a ton of axioms, and there's a lot of stuff to nail down that's a little annoying. But the nice thing about this is that it can be done. Now, the most important contribution of Hilbert to these questions actually comes later when we talk about projective geometry. But I thought it'd be nice to go through these anyway. So what are Hilbert's axioms to totally nail down Euclidean geometry? So he split them into groups. So there's some undefined things: points, lines, line segment, ray, angles, betweenness, congruence. These are kind of the common notions that are undefined, that are taken to be obvious, self-evident. So the first group of axioms is about incidence, that is, conditions for points to be on lines or lines to pass through points. So first incidence axiom is for any 2 points AB, a unique line passes through AB. So that's 2 points determine a line. That was already one of Euclid's axioms. So second one is every line contains at least 2 points. Okay. Third, there exists 3 points, not all on the same line. Okay. So without axioms like this in your construction if your construction requires a point that lies off a line, right, this is an issue if you don't have an axiom like this, technically. And the last incidence axiom is, of course, the most important thing in the whole bit. It's for each line L and point P not on L, there is a unique line through P not meeting L. That's the parallel axiom, or Playfair's axiom. Then the next group is about betweenness or order. Okay, so yeah, it says this is a concept overlooked by Euclid probably because it's too obvious. And this wasn't actually noticed that it was a problem until the 1880s, so, more than 2,000 years later. So we write A star B star C to denote that B is between A and C. So I'm going to read that symbol as B is between A and C. So if B is between A and C, then A, B, C are 3 points on a line, and B is between C and A. Okay, so this is symmetry of betweenness, right? The second betweenness axiom is for any 2 points A and B, there is a point C such that B is between A and C. Okay, so this is basically betweenness as concerned with extending line segments. Or generating a line between 2 points. Okay. The third betweenness axiom of 3 points on a line, exactly 1 is between the other 2. Okay, so when you say 3 points, 3 distinct points here. So 3 distinct points on a line, exactly 1 is between the other 2. The fourth betweenness axiom, so suppose A, B, C are 3 points not on a line, that L is a line not passing through any of A, B, and C. If L contains a point D between A and B, then L contains either a point between A and C or a point between B and C, but not both. This is known as Pasch's axiom. If you want to if you want to see what this is, you draw down draw three non-collinear points, right? And then have another line, okay, that doesn't pass through any of them. If it contains a point that's between one of them, it can contain a point between two of the other pairs, but not both. And the reason why is the line would have to bend. Okay, if you just draw a bunch of configurations where this is true, you'll see that the line would have to bend. So this is an obvious axiom, but it has to be included, or there's some issues. So the next is about congruence of line segments and congruence of angles. So all this is pretty standard. These are basically the common notions that Euclid used. So things equal to the same thing or equal to one another. So transitivity, reflexivity. So this is the reflexive property, which technically is not included in common notions. That you have the reflexive property. This is the transitive property. So all these basically, here's just a list of things that ultimately are the common notions, just specifically for betweenness, for angles, and congruence of line segments. The thing that I mentioned before that was needed technically in the very first construction, two circles meet if one of them contains points both inside and outside the other. So this has to do with intersections of circles. This next axiom is called the Archimedian Axiom, although it was originally discovered by Eudoxus, I believe. So Eudoxus is the one who discovered this axiom, which is saying that, and you might have actually encountered this as, this is essentially the Archimedean property of the real numbers, or the natural numbers. This is the Archimedean property, something that's used in 410. It's used in real analysis a lot. So this is for any two line segments A, B, and CD. There's a natural number n such that n copies of AB are together greater than CD, right? So what this is saying is that no line segment can be infinitely large compared to another, okay? And now this last one, before I mention this last one is not needed for anything you do in Euclid's elements, okay? So none of Euclid's theorems rely on this last axiom. This last axiom is included just so that what we do with Euclidean geometry is identical to the geometry of the plane R2 of real numbers. So if you know anything about some of the fundamental properties of the reals, one of the main things that characterizes the real numbers, you could consider this a topological fact if you want. This is the statement that the reals have no gaps. There's no gaps in the real numbers. So if you are coming at this from like a real analysis math 410 perspective, this is the completeness axiom of the reals. Says that you have all these holes, all these gaps that would be there are filled in. So what would the gaps look like, right? What's the gaps between, say, the rationals and the reals? The gaps are the irrational numbers. So those irrational holes have been filled in the real line, essentially. Okay, and so what does this statement say? It says, suppose the points on a line L are divided into two non-empty subsets A and B in such a way that no point of A is between 2 points of B and no point of B is between 2 points of A. Then a unique point P, either in A or B, lies between any other 2 points, of which one is in A and the other is in B. That seems really, really confusing, and it kind of is. You have to think about this pretty hard. What this is saying, though, is that there's no gaps, okay? Why is this needed? So without this, so if I delete that axiom entirely and I use all the other axioms, what's the difference? The difference is that all the other axioms in question would only give me the constructible numbers, okay, as I mentioned before. But it turns out that even pi, which is a very important number in geometry, pi is non-constructible, okay? And so without this axiom D, technically the area, the space in which I'm doing this geometry, I can't even construct the number pi, right? And so if that bothers you, in principle, then the way to fix this is to include this axiom D, so that the space in question is identical to the real plane. Okay, so that is that. So if you have any questions about those things, you can let me know, either in email or during the next office hours. I believe our next office hours will be on Friday. So I'll send a link for that Friday afternoon. I think I'll actually post about it early, that way you know about it before, like the day of. Okay, so anyway, so that's all the stuff from chapters 2. So now the second pillar, right? Our first pillar was compass and straight edge constructions, Euclidean geometry built up from axioms in this way. So now on to the second pillar of geometry. So this is linear algebra and coordinates. Now this is wrapped up by just saying linear algebra because that includes discussions of coordinates. But linear algebra is our second pillar, because it turns out that a lot of the things I want to talk about, if I stuck to the Euclidean approach, it gets absolutely god-awful. In fact, let me show you just for your own health. If you want to stick to the Euclidean approach, then what ultimately happens, even in Euclid's Elements, so this is Euclid's Elements, this is all 13 books. In Euclid's Elements, things can get fairly nasty, and the arguments are pretty torturous in terms of the diagrams you have to draw, but it's, it can be fairly manageable. But okay. Especially when you move to 3D, moving to 3D. So, Euclid does quite a bit of 3D geometry, and it gets pretty brutal. This trying to axiomatically draw these diagrams, you can see it gets a little rough. This is certainly something I would not want to have to draw on camera, impromptu. And this is, again, this is still in Euclid, so this was not as far as things were taken. That's a nice picture. So in terms of what was done later by later mathematicians, so Archimedes was about 100 years after Euclid. So Archimedes was about 100 years after Euclid, and Apollonius was a few hundred years after that. But if you want to look, so for instance, Archimedes kind of took this about as far as it can go before insanity sets in. So here's this is a good. This is nice stuff. This is actually, so the Archimedean spiral is named after Archimedes, obviously, because he actually computed the area bounded by an Archimedean spiral. But one of the best things that Archimedes did is the following. It's called On the Quadrature of the Parabola, where he is doing this. Right? What is he doing here? You might recognize this. So what was the purpose of Archimedes' investigations on this paper on the quadrature of the parabola? His purpose was computing the area underneath a parabola. And he does it essentially by using the what's called the method of exhaustion, which is more or less Riemann sums. He's kind of like a trapezoid rule, actually, because he's computing the area of these trapezoids. So this is about this was only 100 years after Euclid. So this was 2,200 years ago. So about 2,000 years before Leibniz and Newton invented calculus, Archimedes was using like Euclid's treatment of this stuff to go about this. So this is going to make our lives so much easier. How do I obviously don't need to go through the reasoning behind using coordinates for you guys. You guys have been using coordinates for a long time in your math career. But if I'm trying to think of constructing these, from geometry, how would I do that? Well, I would say I have two perpendicular lines. I don't necessarily care where these perpendicular lines are, but here's a line. And then I have a line that's perpendicular to that line. I don't care anything about where this where they meet, but wherever they meet, I'm going to call that point O. Okay, and that's going to be my origin, right? The idea is if I have an x-axis and a y-axis that are these lines described in this way, then labeling point here is easy, because if I have a point here, using the parallel postulate, well, I have exactly how many lines through P that are parallel to this line that I'm calling y here. Well, there's one, right? So I have exactly one. And similarly, how many lines through P are parallel to this line I'm calling x? Well, one. Right. Now, if I'm living in this nice world where I don't have to worry about these non-constructible things, well, then there is some distance that I call A here. There's some distance from my origin along the line y that I'll call B. And so I can label this point P as the ordered pair AB in this way. Okay? Now, naturally, 2 points are the same if these coordinates are the same, right? So P naught, which is A naught, B naught, and P sub 1, which is A sub 1, B sub 1. These 2 points are the same if and only if the coordinates match up exactly. Right? So I can't swap the order of the coordinates. If I swap B and A here, then I end up with another point, right? Swapping B and A gives me another point in general. Okay, so I don't have to go through all of this. And the idea here being that I consider the reals R as a model for my number lines, the axes. All right. Okay. Now, these are a good model if I have those axioms needed that say that I have filled in the gaps here, right? So then the plane, so this plane defined in this way, this plane consisting of points labeled via ordered pairs. Now, we call them ordered pairs because it matters in what order they arise in. So via ordered pairs AB, the Cartesian plane, named after Descartes, or R2, which is R cross R. Okay. And then that last axiom that Hilbert listed is the thing that makes the Euclidean plane equal to this plane R2, the Cartesian plane in some way. Okay, now you might look at this and you are so used to this that it is something that you don't even give a second thought to, but something as simple as this, you might say, like, how was this something that the Greeks didn't really come up with and flesh out nicely, right? How, it's like, this seems so obvious to describe points in this way. How is it that they didn't come up with this? The reason they didn't come up with this is because they didn't have the algebra to back this sort of thing up. All of the algebra that was done for the Greeks was done extremely laboriously and was done in these really indirect and crazy ways. So, for instance, the whole argument over the fact that the Greeks didn't accept irrationals as numbers that you could actually multiply with or deal with, meant that they had to devote their entire, Euclid devotes in all of Book 5 to the theory of proportion just to avoid dividing by irrationals or multiplying by irrationals. So it was the algebra that wasn't developed enough. They wouldn't have been able to make use of this in a good way because they didn't have the algebra that we're going to use to take advantage of this. Okay. All right. So like I said, this is the way to view this construction coming from a Euclidean geometry point of view. Okay. Now, first things first, right? When I talk about the basics of algebra, well, what's the first thing you did once you had a plane like this, right? Well, points are the basic objects. Well, here's how to describe points. And that's kind of all she wrote as far as how to describe points in the plane. All right, well, now lines. What about lines? So now we want to describe lines in the plane. Okay, how do we do that? Well, you all already very much know that if I draw some line, okay, in the plane, and if I ask you, I want you to come up with a way of representing this line that doesn't just need me to draw something and point to it over and over again, right? I want you to come up with a nice closed form expression that describes every single point on this line without me having to bring this picture with me everywhere. So the first thing that you all might say is, well, here's a parameter that describes a line, right? It's slope, right? The slope of the line. How do you compute the slope of a line? And again, I'm sure it's been drilled in your head at one point or another that slope of a line is rise over run, right? So there's slope, right? What is slope? Well, I can talk about rise over run here. How do I talk about rise over run? Well, I need to consider this in coordinate system. So let's say I have perpendicular lines like this. So we'll call this vertex C, and we'll call this A, we'll call this point B, and then we'll call this angle alpha, and this angle beta. Sorry, I drew an alpha again. This is, oh, that's really bad. So we'll call this beta. Okay. But what if I did a similar thing but used different axes here? So keeping them perpendicular, but now it's a different axis. So here's C prime, and here's what we'll call A prime, and here's B prime. What are these angles? Well, it turns out that if you think about it, these actually have to be the same. They have to be the same because of the parallel axiom. Right? Because of the parallel axiom, they have to be the same. What are these two triangles I drew here? Though they're right triangles, they have these same angles, these same corresponding angles. So I have two similar triangles here. So it turns out that this slope that I want to define is actually, well, this slope is, its key defining property, you might say, that you first learn is that it didn't matter what points you used to define the slope, right? If you picked 2 points on the line, you could find the slope, and it didn't matter which 2 points you picked. How could that be, right? The slope was something that was constant, no matter what 2 points you picked. Why is it constant? By the Thales theorem. Okay. So this is what we'll talk about next time. All right. So on Wednesday, we'll start here. We'll actually probably mostly finish chapter 3. We will get very far in chapter 3 just because our primary approach here is not going to be introducing these things, since you've seen all this stuff before. It is going to be tying in these things with Euclidean geometry and these constructions that we spent a while doing. So anyway, so that's it for today. I'll post your homework later today. This afternoon, I'll post your homework 3. And like I said, office hours will be on Friday afternoon. And I'll remind you all about that. So anyway, I'll see you all on Wednesday.